This video is about the catalytic behaviour of three catalysts: vanadium 5 oxide, iron 2 and Mn2+, Mn3+. The first reaction is the vanadium 5 oxide, and it catalyses the reaction between sulfur dioxide and oxygen, forming SO3, which can be converted into sulfuric 6 acid, which is used in catalysts and other important processes. So what does this catalyst do, the vanadium 5 oxide? It provides an alternative pathway with a lower activation energy, and it all these processes, there's a change in oxidation state of the transition metal, but it isn't permanent, and hence it can behave as a catalyst. So in the first instance, the SO2 reacts with the vanadium 5 oxide, creates SO3 and V2O4. This is now +4 oxidation state, the V2O4. We then regenerate the catalyst by reacting it with the oxygen. So V2O4 reacts with half O2, making V2O5. Now if you combine these two reactions together, you form the overall reaction, because the V2O4, V2O5 will cancel with these same chemicals on the right hand side. So this shows the variable oxidation states of vanadium, going from +5 to +4 and then going back to +5 again. Next is the catalytic behaviour of iron 2 ions. This is a homogeneous reaction, which means it's in the same state as the reactants. The catalyst is in the same state as the reactants. With the SO2, with vanadium 5 oxide, it was actually a heterogeneous catalyst where the vanadium oxide is in a solid state. So what happens in the iron 2 reaction? Well, first off, the reaction between peroxide sulfate and iodide is a slow reaction because you have two negative charges which repel. So the iron 2 or the iron 3, you can do it in two ways, like by adding iron 2 or iron 3. They provide an alternative pathway because it lowers the activation energy. These two react, they have a high activation energy because they're both negative, therefore they repel. So how does it work? How does the iron 2 allow this reaction to take place? So the iron 2 plus oxidizes, and at the same time the peroxide sulfate, which is a +7 oxidation state here, turns to a +6 oxidation state. So it gains 2 electrons, 2 moles of electrons, one for each sulfur, is gained by this peroxide sulfate. Add these two equations here, so it's times 2, because you need to have a balance of the electrons. So there's now 2 electrons there and 2 electrons here. Those two half equations will cancel, leading to this overall ionic equation. In the second reaction, the iron 3, which has been created in the first step, gains an electron, and it then reacts with the iodide, which loses the electrons, and so you need to multiply this first half equation by 2, and therefore you get this overall ionic equation for the reduction of the catalyst and the oxidation of the iodide. So if you combine these two equations together, I'm just going to blue pen, and if you combine this equation here and this equation here, you will cancel out the iron 2 and the iron 3, leading to the overall equation there. Now you can add an iron 3, and this process would happen first, and this process would happen second, but the half equations and ionic equations are exactly the same, leading to the same reaction. The last of the catalytic reactions that you need to be aware of is the manganate reacting with the ethane dioate oxidized by Mn2+. Now this is an autocatalyst, which means that the product of the reaction is a catalyst. So what's the process here? Well, first let's talk about the general reaction. We have manganate reacting with ethane dioate, and the manganate, it is in acidic conditions, so the manganate turns into Mn2+. You need H+ ions and water as a byproduct. So I balance in the order of waters, add the H+'s, and it's 5 electrons. The reason it's 5 electrons is that this is a +7 oxidation state, this is +2. So you need to add 5 electrons to allow that reduction to take place. The ethane diode, on the other hand, is C2O4 2-. It gets oxidized, and it's CO2 plus 2 electrons which are transferred to the manganate at the same time. So to write an ionic equation, you need to combine the two halves together, times this by 2, times this by 5, so that the electrons are balanced. That's 10 electrons being transferred, and that will lead to this overall equation here. Now, the way this reaction works, if you see this happening, is that the product of the reaction Mn2+ actually behaves as a catalyst. So once it's been created here in this half equation, I should say here really, the manganate gets reduced, and the Mn2+ created is oxidized to Mn3. And then to write the overall equation, the ionic equation for that process there of the reduction of the manganate by the autocatalyst Mn2+, we get to this equation here. So you times this one by 5, times by 1, and then you'll get to this equation. Now, I've written a red here because I've simplified the equation. We've got Mn2+ here and 5 Mn2+ there. So it's right and appropriate to cancel the equation. So this is the correct equation that we should have, and I'll come back to the times 2 later. Now, once the Mn3+ has been created, it will then reduce to turn back to Mn2+. It's the catalyst, and at the same time it will oxidize as C2O4 2-. So to combine these two together, these two half equations, we come to this, and there's no simplification once you've multiplied it together. So this is the process of number 1, where the autocatalyst is reacting with the manganate, and this is number 2, where the ethane diode is being oxidized. Now, when you want to combine these two equations together, I'll just highlight these now in the blue pen here. So we need to combine these two together to actually get back to the starting equation there. Now, what you need to do here, if you multiply, you have to think that I've got Mn2+ as a product, but I've also got it as a catalyst. Now, because it's a product, I can't delete all of the Mn2+s like I did in the previous two examples when I'm forming this overall equation. But I do need to delete the Mn3+. The reason I need to delete Mn3+ is the Mn3+ is a catalyst only. It is not a product of this reaction. That's not strictly true. Sometimes we see it as a product, but certainly not on this occasion, and you won't be expected to jot it down as a product here. Most of the time it's Mn2+. So what I'm going to do here is I'm going to just cancel out those Mn3+s. So what I'm going to do is I'm going to times this by 2. This equation by 2 here. I'll get a green highlighter now. So I'm going to multiply this equation by 2. That means I will get 10 Mn3+s on the right. I'm going to multiply this equation by 5. That means I will get 10 Mn3+s on the left. Then they will cancel. So we end up having this as an overall equation. This is the two combined together after the red equations have been combined. When you combine those two together, you then simplify by cancelling out the Mn2+. You've got 10 Mn2+ there, 8 there, so that deletes the 2 here. The 10 Mn3+s cancel, and then that simplifies to the equation which is written here, which is the same as at the start. So this shows that when you combine the two ionic equations which show the catalyst, the behaviour of the catalyst and how it's participating, you get back to this equation. And I just want to highlight to you, it's important you're aware of this for the exam, that you know the shape of the graph with the monitoring the concentration of manganate against time. These are arbitrary units through it. Sorry, not it's time in minutes, but I'm not going to show the scale. It happens over, depending on the concentration, but about 15 minutes. So the reaction starts off really slowly. So this reaction here starts off really slowly. It then speeds up here That should be a plateau. Speeds up because now we've created some more of that autocatalyst. Speeds up the reaction so that the manganate really starts to drop quickly as the manganate is going via this alternative pathway. Then it slows down, the reactant's concentration is lower, the reaction rate also slows down. So that sums up the three reactions of the autocatalyst. First we had thirdly had the autocatalyst, and on the other side we had the vanadium 5 oxide reactions and also the peroxidized sulfate reactions.